talk about a little this model for distributed computation from the thesis of John Chestercliff, which is basically what I'm going to build upon. There are two extensions we will talk about. The first is relatively simple, that is this what I have called quasi-linear case. Then the more general one, which is the non-linear gossip. There are some technical issues which I am going to ignore to just more or less verbally describe it towards the end if there's time. Past till time in, that's the idea. Now this may look like a very, not a particularly major generalization of additive IID noise. So suppose this was independent identically distributed as the standard additive noise model, and I have replaced that by uncorrelated noise, but it's far more general. And the way to see this is that if suppose I had some, instead of this I had some function f of xn comma xn, where xn was the independent identically distributed noise. Now you simply have to define hx as hxn as the conditional expectation of f xn comma xn given xn. Just add and subtract one step conditional expectation and write f of xn comma xn as hxn plus f xn comma xn minus hxn, and club the second and third term together and call it mn plus 1, and it will satisfy these conditions. So it's extremely general, contrary to what it might appear. So general nonlinear noisy measurements can be put in this form just by this trick of adding and subtracting one step conditional expectation. And these are some technical conditions which I won't worry about. Okay, so this is the major innovation which Robinson and Monroe came up with. They sort of foresaw this step size schedule, which just this is perfect thing. It works wonderfully. So they took this time varying, slowly decreasing step size. So it's slowly decreasing because it has to add up to infinity, and the square have to add up to some finite quantity. So for example, 1 by n log n, 1 by n raised to 2 by 3, etc. Will satisfy these conditions. Now what I'm going to use is, the original approach was probabilistic. This Robbins-Monroe work was followed up by several others, like well-known probabilists sort of jumped onto it, like Case Western and Kalyanpur and others. But this is a followed somewhat later in 1974. The approach based on ordinary differential equations due to Derevitsky and Fradkov, and it was extended immensely by Lennart Leung in 1977. And the idea is to view the iteration as a noisy discretization of this differential equation. H dot t is hxt. And if I go back, so suppose this was not there, and n was a constant equal to a, say. So I'm looking at xn plus 1 is xn plus a times hxn. So that's just the Euler scheme, the standard numerical scheme for solving differential equations on computer. So what you have here is this additive noise and a slowly decreasing step size. So you can think of this as a noisy discretization. And what one tries to show is that under suitable conditions, the algorithm will track the differential equation, and therefore have exactly the same asymptotic behavior. So if you have a convergent differential equation, there's a potential algorithm for you. Just look at the discrete version appropriately, and that will give you suggest an algorithm. So that also explains this condition. So I am looking at n as a small, slowly decreasing time step. So what this ensures is that you are covering the entire time axis, because you are trying to capture the asymptotic behavior of the differential equation. So you should cover the entire time axis. So that's ensured by the sum of n being infinity. And the second condition actually ensures that the errors, of course, going to 0, so discretization error will be asymptotically negligible. But it also ensures that the asymptotic error due to noise is the error becomes asymptotically negligible. And one way of thinking, actually what happens is the sum of n times mn plus 1 is convergent under moderate kind of conditions I have stated. I won't get into that, but the results which ensure that the sum of n square being finite ensures that the perturbation noise due to noise goes to 0 in a certain sense. That sense I will probably clarify a little more later. Okay, so I will need this definition that this probably many of you know. So set is A is invariant for the differential equation if it has the property that if I start the trajectory inside this set, it remains inside the set both for positive and negative time. Oh, sorry, you went the wrong direction. Okay. And this is a somewhat more complicated notion. So this is due to Conley. What it means? What I am saying is that if you take n points in the invariant set, and I want this property that given any epsilon positive and t positive, I should find trajectory segments starting at any one of these points in the epsilon neighborhood of any of these points, hitting the epsilon neighborhood of the next point in the chain after some time after capital T. So intuitively what it means is that given any 2 points in the invariant set, you can sort of reach from one to the other modulo these small discontinuous jumps and delay. So you have to spend at least time T in each segment and hit the epsilon neighborhood of the next point. So it start from x0, epsilon neighborhood of x0, go to epsilon neighborhood of x1 after some time after T, then from x1 to x2 and so on, and then reach the other rate. And theorem I mentioned is meta theorem. This is kind of the most general result about asymptotic behavior of stochastic approximation due to a guy called Michel Benheim. What it says that if the iterates remain bounded, which incidentally is not free, I mean, it's usually very hard to check, and then Xn will converge to a compact connected non-empty internally chained transitive invariant set of the differential equation with probability 1. So this AS means with probability 1, and it's the probabilist jargon. It stands for almost surely. So this you can take this, I mean, of course, in most algorithms we are interested in convergence to some desired point, and you can start with this usually and then use the specific structure of the ODE to narrow down the limiting behavior further. So idea of proof is, I mean, I was just given the initial steps. So as I said, the AN is to be thought of as a time step. Okay, intuitively, if you think of it as a discretization of the differential equation, so you can define this new time scale. T0 is 0, T1 is A1, T2 is A1 plus A2, and so on. So suppose AN is 1 by n, then this would go as log n. Okay, so you can see that this is kind of a slower time scale than the actual natural time scale of natural clock n equal to 1, 2, etc. And then I define this interpolated trajectory, just define a Tn, define the trajectory to be xn and interpolate linearly. Then it becomes a piecewise linear continuous function. Then what I do is see, as you might guess that if you want to compare this with a fixed trajectory of the differential equation for infinite time horizon, it won't work, okay, because errors add. So what one does is to take a window, time window of width capital T say, and keep shifting it and compare the interpolated iterates with the differential equation trajectory initiated at the same point at the beginning of that interval. So you keep taking different differential equation trajectories, not a fixed trajectory. So this is the x sub st is a trajectory started at s, which matches with the interpolated trajectory of the interpolated iteration at s. And then for any TA, this is a Gronwall argument basically. It shows that the maximum distance over the interval goes to 0 asymptotically. And the way you do is that because I am shifting the time window, the AN is decreasing. So of course you will get two error terms in the Gronwall multiplying that e raised to kt. And one will be error due to the discretization which goes to 0, it's easy to show because n goes to 0. And the another term is due to noise which goes to 0 because of the martingale convergence theorem which I mentioned. And from this it's quite easy to show that it will go to an invariant set. And you can do the same thing for T negative also, so both positive invariance and negative invariance can be shown. The fact that it's internally chain transitive takes a little more work, but that's also not too bad. So let me come to the next topic, which is the statisticalist model. This was from his thesis in 1986. And his model was that you have a connected graph and you have an irreducible directed graph. And at each node you have one processor agent, and I'll denote by script ni the neighboring nodes for I. And then you have the stochastic matrix Pj given I, which is compatible with the graph, so some irreducible stochastic matrix. By that I mean that Pj given I, you can think of that as probability of going from I to j, as in a Markov chain, except there is no Markov chain here. So this is just some weight with which you are going to average. So these are quantities between 0 and 1, and summed over j they add to 1. So j given I summed over j is 1, and this was his algorithm. So if this was not there, and if I just had xjn, then it would just be a stochastic approximation, the usual stochastic approximation. Okay. So what the change here is that the idea is this. So this ith agent has his own computation here. This can be more general actually, can involve the neighbors also. But anyway, there is some computation which h can also depend on I. There are various generalities one can think of. But anyway, so xi he has this own computation, but instead of using his own previous iterate as the starting point. The stochastic approximation looks at the previous iterate and makes a small incremental correction. Here you make an incremental correction not to your own previous iterate, but to an average value over your neighbors. So the first is actually, if I just ignore the second component, that A in term, then it's just plain averaging. That's called gossip. At least one of the gossip. There's a vanilla gossip for computing weighted averages in the distributed. For example, if you want to compute average temperature in some disaster zone over sensor network, then this is the kind of thing which can be used. And people are, of course, the convergence there is a linear, just averaging, so it converges to some constant value. That's not hard to show, but there is a lot of work has been done on how to choose the stochastic matrix, usually doubly stochastic, so that the convergence rate can be optimized. So that doesn't concern us here, but anyway, just wanted to mention there's a lot of work on just this aspect alone, the gossip aspect. But here it's not pure gossip. There's the second part is typically a learning algorithm or optimization algorithm. So you can think of the statistical scheme as a combination of gossip and learning. As I said, there are a lot of painful issues which I am going to talk about later. Because it's a distributed scenario, there can be a lot of delays and the computations can be asynchronous, etc. Now there are similar objects in other disciplines like synchronization, flocking, coordination, etc. And there generally the objective is consensus, that all of them, I think there are a lot of talks on it, this session on consensus, so you are familiar with this, that all the entities should follow some common velocity or something like that. This has a similar flavor, what I am going to do, except that nothing is moving, so just the geographically fixed agent, so the problem is easier for me. And there are standard approaches. I mean, there's an extensive amount of work on this kind of things, particularly this statistical scheme there's a lot of work by, for example, there are full-fledged books in this now published series one by Angela Nedich and one by Ali Syed, and I think also one by Vikram Krishnamurthy. So quite a lot of work already. And the typical approach is to use the fact that if you just do iterated averaging, eventually all the values have to become equal. So at least the probability crowd tends to use this somewhat old paper from Journal of Applied Probability by two statisticians, Chatterjee and Sinita, which gives such results. And another approach which some people have used, which the probabilists among you might like, is something called coupling from the past. So those of you who are familiar with the Prof-Wilson algorithm for exact sampling, what you do is you initiate a Markov chain for every possible state from some distant time in past and let it couple. So when the two meet, you just take them together. And you keep going back in time, eventually all of them will meet at some point. And if that happens, that point has exactly the stationary distribution. So unlike Markov chain Monte Carlo, which goes forward in time and asymptotically gives you average with respect to stationary distribution, this gives a sample which has exactly the stationary distribution. So that's called Prof-Wilson algorithm. So basically what it means that two Markov chains started sufficiently far back will eventually meet, would have made by now with high probability, let's say. So that's another approach. What I'm going to do is to take a third viewpoint, which is to, as I said, treat statistical scheme as a regular perturbation of a standard gossip with 2 time scales. So the gossip, if you just consider xn plus 1 is p times xn, where p is the stochastic matrix, it's a marginally stable system because this whole the Perron-Frobenius eigenvector is a vector of constant. That one-dimensional subspace is invariant subspace. That's not a point attractor. So the way one can think of it is that the gossip component, which is on the first time scale, ensures convergence to the one-dimensional subspace of constants, which means consensus. So this part, just if you are interested only in consensus, this part is enough. But then once sort of restricted to that, the slower dynamics picks the exact attractor in that one-dimensional. So I will talk about the first case, which is kind of a small generalization, but it's interesting, as you will see, for a variety of reasons. So here we simply allow this to depend on the current iterate and the various assumptions. This means that it's either 0 or bounded away from delta. So if it's positive, it's bounded away by at least delta. The transition probabilities are uniformly positive or 0. And you can allow things to, as I said, you can allow the argument of the H function depend on the neighbors, but the math doesn't change if I make it even more general, though doesn't fit the model that it of distributed algorithm because it assumes that you know everything. It doesn't affect the math, so I'll leave it. I'll just let H depend on everything here. Namely, I replace this by xn. So I've allowed H indexed by I. So it's a function. Each I has a separate function hi, but the argument without loss of generality can be xn. And the consensus is that, of course, this is the Chatterjee-Seneta kind of argument will give you, that all the components will asymptotically approach each other. And main result is for the, I'll first state for the one-dimensional case because it's easy to write. You consider this set script A, which is basically the vector, constant vector, the one-dimensional space of constant vectors. And if the iterations don't blow up, then this will converge with probability 1. So this will track basically this averaged differential equation. So it's kind of a dynamic consensus. They all the same trajectory of the same differential equation. And the differential equation is given here. The average with respect to the stationary distribution of P sub y. So generally, if in the Chesclays case, this y wouldn't be there. It's just you get average with respect to stationary distribution of a fixed matrix. And this is the multidimensional case. It's just notationally a mess because each of these is a vector, but it's the same thing. And then I have Benheim-like theorem that Xn converges to a compact connected non-empty internally chained transitive invariant set of the n-fold product of the dynamics, that is n copies of the same dynamics. And starting with this, you can get stronger results. In fact, for d equal to 1, if you have a well-posed differential equation, scalar differential equation with bounded trajectory, it has to converge. So you get convergence for free in many applications, assuming you are working with each guy as a scalar computation. And one thing which we applied it to was this scheme. So took hi to be minus grad f. So for the pure stochastic approximation, it would mean a stochastic gradient descent, which is a very popular paradigm in machine learning and so on, neural networks and several areas. And the f we choose to be this particular thing, which comes from Metropolis Hastings scheme for Markov and Monte Carlo. So this has the property you can check that it's a reversible. It's a transition matrix of reversible chain with this as the stationary distribution, which will put more mass on lower values of f. So the algorithm itself, so this dynamics itself, individual dynamics trying to minimize f, and on top of that, this averaging scheme is putting higher weight on low values of f. So it kind of further reinforces the minimization. And it was sort of motivated by this PSO literature. I'm not an expert on this, but some variants I had seen, this particle swarm optimization. What they do is each agent decides the movement depending on his own information, like gradient, his neighbors, and then they have some leader whom they follow, whoever is doing the best till now. And that component is non-local. Whereas this scheme is local, it just readjusts weight through local computations without having to keep track of who is the best. The weight will, just because of this time scale effect, 2 time scale effect, it will automatically put maximum weight on the best performer. And I have not put any graphs extra, but we tried this on the standard library of bad functions like Rosenbrock function and Grevank and whatnot. And there's lots of 1 and 2 dimensional functions with multiple minima and each with its own peculiarities. And of course, this doesn't guarantee global optimum, but it does better than just a naive optimization schemes. It gives a reasonably good local minimum. Okay, so this I already said. Think of it as a 2 time scale, and gossip is on the fast time scale, which is just the standard clock in the background, and learning is on the slow time scale, given by the step size n. And there also has been work on 2 time scale algorithms of this variety. This is different from what I am doing. Here you have split the entire iteration into 2 sets of indices, some with step size a and some with bn, and bn goes to 0 slower than n, so bn by n goes to 0. So this also has a similar effect, but this is actually corresponds to a singular differential equation. So the limit, it's basically mimicking a singular differential equation, so the analysis is different. There's something else which I'll skip. I mean, there's also, this is closer to, sorry, not this, our algorithm is closer to what's called Markov noise. This is what Lennart Ljung had introduced. You can have additional process here and you get the average with respect to that. So it has some technical similarity with that. So you can also give a stability test. But actually, this is adapted from some earlier work I had done with Sean Mine. So you look at the scaled. So suppose this is the right hand side of the vector field driving your differential equation. You scale it and let's see go to infinity. Suppose this limit exists. Okay. And then it will inherit the Lipschitz property from the original H. And you look at the scaled differential equation, and if this is origin as the asymptotically stable equilibrium, then the iterations don't blow up. This test is easy to apply for most reinforcement learning algorithms. And the idea is that, because I am sort of scaling this, what happens is that if the iterates start blowing up, then a normalized version of the iterates will start tracking this equation. And if this is stable, that means if they go far away, they are forced back and therefore cannot blow up. That's the rough intuition. So I'll talk about the more general case, which is the fully nonlinear. We simply replace the average with respect to P by full proper nonlinearity. And cannot be arbitrary. I don't know, at least we have considered only a limited class tilde. Perhaps one can do more. And assume that you just iterate f. So consider xn plus 1 is fxn. It will converge to this function p of the initial condition x, which has to be basically a projection. And then capital C will denote the set of fixed points of this operator p. And so for the first work we did, in this particular work, we assumed a lot of technical conditions. So that assume that it's Fréchet differentiable and the Fréchet derivative is Lipschitz, etc., and some higher order moment condition. That's mainly needed for the proofs, and nothing. That can probably be relaxed. And the main result is that Xn converges to a compact connected, that means a Benham-like statement, non-empty interchange transitive invariant set contained in this set of fixed points. So this is a generalization. So the set C of fixed points of the nonlinearity replaces the invariant subspace of P. So we are motivated by projection to a convex set. So if suppose I have if you are doing some projected algorithm and you have this iteration to calculate the projection, then you can sort of interface this. So typically what one does is each step you compute the projection separately and plug it in, and so approximately compute the projection, plug it in, go, then do the next iteration. But here you can do it concurrently. You don't have to separate doesn't have to be a subroutine. You can just separate the two processes on two time scales and run them concurrently. So what you need, because this is meant to be a distributed scheme, you need a distributed scheme for computing projections on, for example, intersection of convex sets, which is a common scenario. So I'll return to this later. Turns out that many of the strong conditions I imposed don't work in this case. So there's some more recent work I'll talk about which gets around that. Okay, so I'll talk about very briefly the messy issues. I mentioned that this is a distributed computation. These are the problems. This interprocessor delays, then not all updates may be done at the same time, and each agent may have a different clock. So let me introduce some notation. So suppose this can be, for example, event driven with different clocks, etc. But one can club things together as a simultaneous event without loss of generality, as long as you are not abusing causality. I mean, you are not putting something which if xn is contributed to the computation of xk, you shouldn't put that out after k. So some basic discipline is observed, then you can pretend that at each time n you are just updating a subset of nodes n. So I call that Bn. And nu in is this is essentially the local clock of agent I. So number of updates till time n, which so the agent I doesn't have to know n. He knows, but he knows nu in, he knows what he has done. And what I need is that the clocks are comparable in the sense that the updates are done comparably often. So there's some non-zero fraction of the background clock at which each one has been updated. And these are the delays. And one has to impose some conditions. And let's assume they're bounded, and some movement condition will do. And then you also need extra condition on step sizes. So as I said, if the step size is 1 by n, then the cumulative sum of ai goes as log n. Then this will be true. So this is just the sum of Bn. I called it B here. So this is sum of Bn. If B is 1 by n, then this goes as log n, and this will be true. You can see that this log alpha n by log n goes to 1. This is true for example, 1 by n log n by n, etc. but it's not true for 1 by n raised to 2 by 3. So it's not, it doesn't follow from the Robins-Monroe condition. There's some additional restriction. And maybe I can describe the role it plays right now. So what happens is that if suppose two agents I and J are using their own clock, and suppose I did his iterates only half the time, and half the time he was sleeping, and J did his iterates only 1/3 of the time, then their time, actual local times will evolve as tau n by 2 and tau n by 3. But if this is true, then tau n by 2 divided by tau n by 3 asymptotically approaches 1. So their timescales asymptotically match, and that's good enough. So that ensures, okay, so one has to replace this by, one has to make this computation also incremental with the different time steps. These are the delays, so forget this. These are the number. So this is 1 if I is in Bn, that is if ith component updates, then this is 1. If it does not update, it's 0. So this is just some notation basically. The intuition is not harder, but to write down both the statements and the proofs is a pain. So the intuition behind, so delays don't affect, because this is actually true in general in stochastic approximation, assuming that they are not too large. So they get squeezed out, and the intuition, as I said, is very simple, because if you recall the proof of convergence, I had taken a fixed width interval of width capital T and slided it towards infinity. So from S to S plus T, say, and let S go to infinity. So now my time scaling from real time to algorithmic time is, suppose I use step size an is 1 by n, then the time scaling is n to log n. So any time interval of width t in the algorithmic time scale gets mapped into something which becomes smaller and smaller. Okay, the ODE you are comparing it with is on the algorithmic time scale. So it evolves less and less in that time interval. So the error due to delays asymptotically goes to 0. This is not a problem at all. The bigger problem is the asynchrony and local clocks, etc. So if I had used, see, I used this step size, maybe I'll highlight that. I used, instead of using Bn, I used B nu in, instead of An, I used A nu in. So this of course makes sense, because this means I doesn't have to know n. He just can use his own clock. But this is the other advantage, that because of this and the condition I imposed, you get basically you get a limiting ODE where which is the same as the original modulo some time scaling. This is a constant scalar you get on the right hand side, and it doesn't matter, because it will only affect the speed and not the trajectory. So if you have x dot equal to hxt and x dot equal to a times hxt, where a is a positive scalar, they have exactly the same trajectories. Only the speed is reduced or increased depending on a. So this trick works, and you get again get the convergence back. For some special cases like stochastic gradient, one can relax this, but not all. Stochastic gradient and this max norm contractions, you can relax this. So there's some, we have given a stability test, but I think a better stability test would be welcome, and more general scenario. And this is something my student is looking at, is trying to use this for. So basically, if you want, there's a lot of these optimization algorithms on matrix manifolds, etc. to whether one can, so ideally you would have to keep projecting back. So can one replace that by some faster time scale iteration like this and do the same? So this is what I want to talk about. This is some recent work by a PhD student. So there are a lot of applications of stochastic approximation which look at projected stochastic approximation. So this is studied extensively by Kushner and Clark. So the differential equation you get is this, where pi bar is the, so pi is the projection to projection operator. Suppose you have a convex set, each time the algorithm, the iterate goes out, you project back, and they assume that this is a Frechet differentiable, and the ODE you get is this. More generally, you get a differential inclusion that also has been analyzed. So our idea was to replace this by this 2-time scale. So to start with, you need a fast distributed scheme for, so the specific case we looked at is the projection on intersection of convex sets. So there's some, this is algorithm called, been around actually, by Boyle and Dijkstra actually did it in some statistics context, and it was rediscovered later by Hahn, and it's called Boyle-Dijkstra-Hahn algorithm. So you need a distributed version of that, and then you do stochastic approximation on slow time scale. And this actually was done by a B.Tech student, now doing Ph.D. in Berkeley. It's called Soham Fade. This is the advantage of being in IIT, and sometimes B.Techs also do wonders. And so, okay, I think I am more or less done. So I have not given details here, but this Soham Fade had provided the distributed version of the Boyle-Dijkstra-Hahn algorithm. So essentially, I should mention that if you are projecting on intersection of subspaces, then you just keep doing alternating projection, it will converge. That goes back to von Neumann, but that's not true for convex sets. As one can give easy counter examples. So this is a non-trivial scheme you have to use. And there was a parallel version due to USM and DPRO, and what we did is to use that and make it distributed. And so use that, then the final scheme uses this on the fast time scale and the stochastic approximation on the slow time scale to prove convergence. So these are the three things. This has already appeared, the nonlinear gossip part. And this is hopefully will appear, already gone through two revisions in fact. And this is submitted very recently, so it's a long way to go. I think that's it, yeah.